Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Welcome to Whimsical Wavelengths, where everyone comes to hear sunny quips and cloudy chuckles. Yes, we here at Whimsical Wavelengths are amazing at precipitating a good story, and I am your host, Dr. Jeffrey Zurich. If you haven't guessed yet, this episode's all about the atmosphere, more specifically, climate versus weather, and the increasing extremes. It might feel odd that a science podcast would take so long to get around to a climate episode. Well, it is in part because the science and the data is overwhelming. Humans have changed the chemistry of our atmosphere, which is causing it to change. That's an observable fact. No political beliefs or anything else in that. What to do about it, that is political. Generally, and there will be caveats, I plan not to get into the politics of things, but perhaps I would have more listeners if I did. This is one of those science topics that for some reason crosses that political line. There's so much we can tackle with respect to climate change, and much of it has been alluded to or is part of our everyday conversations already. It's extremely well covered. However, sometimes it's not covered well. Besides today's episode, I am working on putting together an additional episode on climate using climate proxies like ice cores, foraminifera, tree rings, and the like. In the near future, time is geologic. I haven't put a deadline on that just yet. More broadly, climate change is also a topic I push back against on social media, against those who wish to believe doesn't exist or is completely not a problem. 99% of the time, that conversation is not about the data or the science, sadly. Conspiracy theories and people who try to ignore this problem make it about people, money, and power instead of the repeatable observations and data. One thing that does get mixed up often is weather and climate. And that seems to be a common one regardless of one's beliefs. On one level, the difference is very simple, based solely on definitions. Weather is the state of the atmosphere at a specific place and time. Is it raining right now? What's the current temperature, wind direction, and speed? In other words, do you have a window? Open it. Climate is the average conditions for a specific place over decades. Usually, we use 30 years or more to average across. For instance, climate-wise, the average chance that it rains on any particular day in January in Vancouver, British Columbia, Canada is close to 50%. And the total rain for the month of January averages to about 190 millimeters. That doesn't take into account any individual events, it's just the averages. And yes, it rains here a lot in winter. Raincouver is another nickname. Climate change is changing those averages. Vancouver's daily temperature has increased on average by about 1.4 degrees centigrade from 1900 to 2013, higher than the global average. Obviously, changing those averages will also change weather. However, the exact link between a specific event at a specific time, weather, and climate is more nebulous. To help break it down, and how climate change affects our weather and the associated hazards, I've brought in an expert, someone who's used to communicating about this. Today, we are going to have Jared Rennie, a research meteorologist, to help us tease out how our changing climate affects us. So I want everyone to welcome Jared Rennie, a research meteorologist from NOAA's National Centers of Environmental Information. Listing some of his professional highlights from his career, he's laid the groundwork for the evolution of products and services that link weather and climate information with socioeconomic impacts. Lead as the project manager for the State of the Flood program, served as the senior technical coordinator for long-ranged research programs and projects of national and international significance, including the Global Historical Climatological Network. I often trip over words, as listeners probably know. from the NCLIM Grid Daily and the 1991 to 2002 normals. So thanks for being here, and it keeps me from getting way too far over my proverbial skis, especially as Vancouver just got snow for the first time this year.
Well, thanks for having me, and don't worry, I will trip over my words and acronyms as well, because we love our acronyms.
Boy, do we ever. But we'll try to make sure that we explain them and make sure that everything makes sense, that we're not talking in acronyms. But to start, let's start with climate. You've read the intro that I gave. Climate is a long-term average. For one measurement point at one location, anyone can do that in Excel and get an average. Finding the world average seems like an undertaking. What are the measurements that go into that average? How are they done? And also free to add more to my simple explanations that I did in the intro.
Yeah, sure. So, it's funny. When I first came here to NOAA about 15 years ago, one of my colleagues initially told me, taking the temperature of the Earth is a lot harder than you think. And I was like, that can't be true. We just use thermometers and get the temperature, right? After all these years of kind of being into the thick of it, yes, it is very complicated. There's many different sort of processes that go into the global temperature average, and there's multiple ways of doing it. Here at NCEI, we kind of use two different types of data. One is what we call sort of on the ground land in situ measurement. So an easier way of saying that is like weather stations. So weather stations at airports and volunteer observers and other national weather services across the world, they have many different ways of installing just, thermometers on the ground. So, and they're depending on the network, they're located at different areas, different heights, different types of measurements. But long story short, they all basically just calculate, temperature every few minutes. So what happens is every day they get sort of logged and sent to the National Weather Service. And then they end up here at NCEI, which is headquartered in Asheville, North Carolina, USA. And we take that data every day and we sort of do some aggregation. That's kind of the first thing, is that we aggregate it up to different levels. So
and
one of the
aggregation means.
So in this case, we're aggregating it by time. So depending on the data set, so it might have temperature every hour. So we'll aggregate that or kind of take the average for a day. And then from daily measurements, we'll sort of average that up to a month. So, and depending on the data set we're talking about, so, one of the acronyms is GHCN, which is the Global Historical Climatology Network. There's different versions of it. There's an hourly version, there's a daily version, and there's a monthly version. Most of it's pretty much integrated across the three, but if you go to our website, you might notice there's different time versions of it, and they get aggregated temporally into these sort of averages. We follow, by the way, I should mention, since we're talking about aggregation, we follow methods by the WMO, which is another acronym, the World Meteorological Organization. They're headquartered in Geneva. They have many different guidelines for doing sort of this aggregation or averaging, and NCI, we sort of follow that. We are getting into the nitty-gritty of things, but we essentially take the monthly versions of these, and which is about something like 25, 30,000 stations across the US. And this is just on the land right now. And we do some quality control and bias corrections to that data. And then we kind of come up with sort of a land average of what the temperature is for a given month. So now we're only talking about the land portion so far, which is about 30% of the Earth. So obviously most of the Earth is ocean. So we also have ocean data across the entire globe, and that includes that's a different data set from our website. It's called there's a few versions, but the one that I'm talking about is called ERSST, which is Enhanced Reconstructed Sea Surface Temperature, and that is they're from, again, many different sources, but buoys across the ocean. Very similar methodologies of ingesting the data and doing some quality control on it. And then they kind of just get merged together, the land and the ocean, into something that we call NOAA Global Temp. And then we do some extra quality control on it to make sure it's sort of consistent across the board. And then that's basically our reconstructed global average for, in this case, for a given month. And then we sort of compare that month to the historical record, which I believe goes back to 1850. And then that's how we get the sort of our individual value, X degrees Fahrenheit or X degrees Celsius, and compared against some sort of climatology to say that, was it warm, was it cold, was it the warmest on record, was the coolest on record. That was a very quick and dirty version of what happens.
That was also a lot of jargon, but you explained it all, but it came in rapid fire. Holy smokes. So I have some follow-up questions. Just out of curiosity, to start with, the easiest one to answer of the follow-up questions, how many years do we typically use to define climate? I think people use different amounts, but let's say your organization, for instance, probably uses a set number.
Yeah, the World Meteorological Organization defines climate, or like a climatology, which is sort of like a reference period to compare values against. They define usually a 30-year average. So the most recent one that a lot of folks use is the 1991 to 2020 average. We utilize that. We also utilize what we call the 20th century baseline, so it's 1901 to 2000. And then there are others, I believe, in Europe. They use the pre-industrial period as well, which I believe is from 1851 to 1899. There's many different versions, but typically at a minimum 30 years.
I see. Okay. And this part is perhaps one of the more interesting parts to me, is like the sausage making, so to speak, in creating these data sets. I guess you can say you alluded to them, you've mentioned them, but they're standard procedures, right? Like, you can get into the details of QA/QC perhaps, but they are standard no matter where you are, which institution you are, right?
Yes and no. So the data set, all the methodologies that we're talking about is through NOAA, which is the National Oceanic Atmospheric Administration. We have a set of quality control and bias corrections that have been through peer review. I'm happy to provide those papers to put in show notes. And when there's kind of two parts to it. The first part is just your typical quality control. Like, is the station within, does it make sense? So, if a temperature value is recorded as 1,000, obviously we don't want to include that. So we throw those out. And those are generally consistent across all the organizations. There's another piece called bias corrections that we do. It's a little bit different than quality control. What it does is it looks for these very small shifts in temperature changes as a result of non-stationarity. And what I mean by that is things like if a station moved from, let's say, one side of the airport to the other, it may, in a normal, like, one day, looking at the typical weather, it may not make a big difference. But when you're looking at long-term averages, you might see these shifts, these biases of, like, let's say 0.1 degrees Celsius. And those are basically values we don't want to put in there. So what we'll do is we'll go find those. We'll find these statistically significant changes over long periods of time, and we'll sort of correct for that. It's through an algorithm we call pairwise homogeneity. And that, again, that's based on peer-reviewed literature. Now, to answer your question, there are multiple organizations that do the same thing. So, for example, NASA does their own version of this sort of global temperature calculation. There's another group in Europe. There's a few out there, one through the UK Met Office, one through the European Union, which is known as Copernicus. And then there's a few others as well, Berkeley Earth, Japan Meteorological Agency. They all pretty much use the same standard inputs, but they do have their own different methodology to kind of get to the answer. They have, again, still peer reviewed, but they come up with their own sort of algorithms to do the bias corrections and the quality control. And the big point here is that, yes, there are different methodologies, but they all pretty much come to the same conclusion.
Yeah, that was exactly where I was hoping to get to, and we kind of jumped ahead 3 questions. Yeah, so that makes a lot of sense. All right, so thanks to your wonderful explanations and going through and showing that like everywhere may have slightly different methodologies, but they're all based in data science, and they all come to the exact same solution, plus or minus a tiny insignificant bit in comparison to what the general trend of the data is. So now to describe it and fit it into what we understand. In other words, how's it going? Under the assumption the globe is developing a fever. Okay, that's a terrible analogy, but seriously, what is the data saying for the globe?
Yeah, it's not the greatest analogies, but that's okay. We're the long and the short of it, we're recording this in January 2025, so we're recording this in February 2025. So at the time of recording, we just did our analysis for 2024 for the whole year, and all the organizations, NOAA, NASA, Copernicus, they announced that 2024 was the warmest year on record. It almost seems like we're saying that a lot. Every year we seem to be saying that, X year was the warmest or the second warmest or X month or X season. It's getting it's hard to say it over and over again. I'm kind of getting sick and tired of saying it over and over again, but it's important to understand because the world is warming. This is climate change in action. Temperatures have risen over the past 30 years. And according to the NOAA data set, the top 10 years have been the last 10 years. So, needless to say, it's been warm. Now, how warm? Only a degree or two above the average. And this comes back to science communication a little bit, where people might think, oh, it's only 1 or 2 degrees higher. That's not a big deal for me. It's just a couple of degrees, it's not a big deal. But we're talking about global average, which means that there are other regional parts of the world that are much higher, like 5 degrees, 10 degrees above normal. And that is very concerning. And that's also to say that there are some spots of the globe that are cooling. When we're under La Nina conditions, there are parts of the ocean that are cooler than normal. But looking, geographically, spatially averaging across the US, or all over the world, it's still pretty warm. So it is, unfortunately, much warmer than it should be.
Yeah, which is another reason why I want to dive into this in the future, finding someone who can do climate proxies and kind of go into that in much more detail. So I do spend a fair bit of time on social media, arguing, I guess, or trying to discuss data about the top line numbers, because they're concerning, they're alarming, they're worrisome, and it's not good. What is your go-to data set to try to discuss this with people that maybe are trying to suggest what you said, that it's just 2 degrees, it's not really worth worrying about?
Yeah, that's a good question. There's not a silver bullet here. There's not a one data set to rule them all, to kind of tell people that this is concerning.
For sure. But there must be something you find that's easier to communicate that. There's definitely not a silver bullet, and anyone who suggests there is crazy. But there must be something you find is easier to communicate what's really going on and the power of what's really going on.
Yeah, so there's 2 that I'm thinking of or at least one actual data set, and then the kind of the second piece is a little bit different. But we'll have people that'll say that, first off, they'll say, hey, this is not as bad as we think it is. It's a degree or two. Or they'll even start questioning the methodology. There'll be folks that'll say, like, how did you come up with this? There's error bars, or you're changing data to tell a story. Usually with that, I'll tell people a few things. One, I'll say, look at all the different data sets with the different inputs and the different methodologies. Like that's kind of a good thing that NASA and Copernicus and others do different methodologies, because they're different. I keep saying it, but there's different ways of doing it, but comes to the same conclusion. So there's that. But you still have people that are like, oh, your input data is all messed up and blah, blah, blah. I would point people to, I had mentioned there's folks at an organization called Berkeley Earth. About 15 years ago, they came around through, I believe it was the University of California, Berkeley. Might not be 100% sure on that, but there were some professors there that were very much unsure of our methodologies. They were like, we doubt that this is happening. We doubt your data methodologies. We believe your inputs are wrong and everything's wrong. And we're going to come in and do it correctly. We're going to bring in the greatest scientists, the greatest statisticians in the world. And we're going to do our own methodology, and we're going to prove that you're not correct. We're going to prove that, the Earth is cooling, and we're going to prove X, Y, Z. So they came and visited, and we chatted with them, and they had really good questions, and we helped them as best as we could. But they went off and did their own analysis, and about a year or two later, they came to the same exact conclusion. So they're like, oh, we did our own studies, our own methodologies. We built our algorithms from the ground up. We removed data that we thought was questionable, and lo and behold, it was the same exact result. So they have since sort of changed their tone a little bit, and to this day, the results that we produce, they still produce. So that's kind of a way of saying, like, hey, there are non-government versions of this, or non-national versions of this, to get to the same answer. So that's one. The other piece too is, and this is where, and I know we're going to talk about this later, but this is where being a science communicator is really important, because it's important for us to talk to folks about this, but at the same time, it's very important to sort of listen and understand the people we're talking to, or the organizations we're talking to. What do they care about? I may not go, I don't want to go to a group and spew 7 things about climate change, when in reality, they're focused on, only one of them or something different. And that's kind of what I was getting at, that there's not one data set to rule them all, but if you listen to your group that you're talking to, and understand this is where empathy is important, understanding where they're coming from, what they're getting at, and then kind of helping them get to that conclusion with a data set. So for example, like agriculture, they might care about drought, or how wet or how dry the soils are. So if that's the case, I will go and say, hey, here's a soil moisture data set you want to look at, or some sort of drought monitor you want to look at, versus maybe somebody in the insurance industry that it cares about disaster risk. And it's like, okay, well, maybe we want to talk about the economic impacts of climate change. Does an event hit $1 billion, let's say, or or are people vulnerable to events? Underserved, under risk people. That adding vulnerability data is super important. So it really, I'm not sure where I'm going with this, but they kind of just like, it's important.
You're trying to make it personal to them.
Yeah.
Like, you're trying to connect to them on a personal level, instead of what as scientists sometimes do, which is a bigger picture, kind of impassionate, like it's devoid of self almost, especially the way we write science, right?
Yeah. That's true, because and that part's still important. It's still important to write our research,
absolutely.
to publish research, but relating that to the public is super important. And I find that piece really, I believe there's a professor, he's at the University of Georgia, his name is Dr. Marshall Shepard. He has talked about something called kitchen table issues. And I think that is the way to come at it, is to understand maybe, knowing your audience. The climate stuff I speak to you is different than what I speak to kids in ninth grade is different than what I speak to my parents. And it's
But the
super
data is
important.
always the same.
Correct.
That's the key. The message might be slightly different, but the data is always the same.
Yes. Yes.
Okay, well, we've been talking so much in a global sense, and then we've already started the pivot to try to talk about it to the person. So coming back, let's I think, as you just said, the story is experienced locally. So to go from the globe to the US and then perhaps even closer to your home in North Carolina, how does going local affect the data?
Yeah, it's, I had a colleague about 10 years ago say something to me that was like really, it's like a mantra that I really live by this to this day. We were having lunch and we were talking about the recent climate assessment that came out from the US National Climate Assessment. This was in 2014. And there was a conversation, especially where I'm in North Carolina, talking about sea level rise, because North Carolina, there's parts of North Carolina that are on the coast. And we were talking about sea level rise. And I don't remember how we got to a certain part of the conversation, but a colleague of mine said, Jared, nobody in Iowa cares about sea level rise. And I thought about it for a second because, like, one, from a geographical standpoint, Iowa is a landlocked state, so there's no coast. So they're not going to care about sea level rise. But it kind of led to a deeper meaning for me of like kind of going back to making it local. Even in North Carolina, I'm a part of the mountainous parts of North Carolina in the west. So when I have people think like, oh, well, there's a hurricane hitting the Carolina coastline, are you okay? I'm like, I'm an 8-hour drive from the coast. So the sea level rise or ocean things don't necessarily affect me, but flooding does, let's say, especially in the western part of the state, or snow because I'm in mountainous areas. So making it local is super important. And it kind of comes back to the kitchen table issues. You can say, for example, let's say in the northeast part of the US, last winter season, there was a snow drought, meaning they didn't get as much snow as they expected. And while I may not care because I'm in the South, may not get as much snow, it's important for them because, that's one of the signs of a warming climate. Temperatures are rising, ergo, snowfall is decreasing, typically speaking. So it's really important and it's hard to do because, again, you have to tailor your audience to whoever you're talking to. So if you're talking to 17 people in a given week, you have to tailor it to 17 different stories. And again, it's hard to do. The data's the same, but just tweaking it to get the person you're talking to act upon it. I generally think that we do a good job with the physical science of all the modeling, all the climate data, all the climate change science. I think is pretty good, but just getting people to act upon it, that's the harder nut to crack, I think. And it, like I said, it comes back to science communication. It comes back to tailoring it to every unique experience. And it's hard, but it's important to do.
Yeah, for sure. One of these days we'll get around to actually figuring out what to do about it. But in the end, we take all this weather data, we average it, we strip out the daily variations, we look at the long-term or long wavelength trends. It always comes back to wavelengths. How do we then use that information to talk about this weather that is affecting us locally? Because that interchange between climate and weather sometimes is reported on in the media and used even sometimes by scientists when they're trying to communicate quite poorly.
Yeah, because this comes back to, weather versus climate we have a lot of different metaphors for it. And I'll be honest, it's hard to explain too, because weather is a current point in time. It's like today's weather, so for me, example, it's a sunny day. It's actually warm today, high of 70 degrees. But climate is sort of the long-term average of things. So like what we expect on a given day is, so like we expect in early February, the high temperature where I live is to be about 50 degrees. But in fact, it's 70 degrees today. So that's sort of the difference between weather and climate. Climate is what you expect, and weather is what you get. So again, we expect it to be 50 today, but it actually is 70. So that's kind of one quick way of doing it. It's also, especially, we're recording in the winter months, so it's always hard, especially with climate change, when you have a snow event or it's really cold. A good example now, the data's not out yet, but we know that January of 2025 was fairly cold in the US and parts of Canada. I mean, we had single digits down in the south, which is very rare.
Thanks to a polar vortex, right? Like
that's part of it, yeah.
So the point is that there was a weather phenomenon that happened that brought cold air south, that changed our weather. But my question is more like, sure, we can use the cold weather because that's what we're living through right now, but also just in the events that come up, like could be hurricanes, could be heat, could be drought, and then using the changing climate to discuss these events seems to be poorly done recently in most media. And that's kind of where I was trying to go with this question, is like, what's a good way to actually use the fact that we have all this information that we've kind of talked about already and how it's built to then discuss these larger events or that happen locally, right? That's what we feel. So how do we use that climate information to discuss the weather that we're feeling?
Yeah, so that's partly something what we call climate attribution is, are these particular events, out of the ordinary? You take the cold snap that we just had, and people will go, oh, well, so much for global warming, right? Because it's cold. Well, that's not exactly the case. So what we'll do is, let's take something more disaster, like a wildfire or flooding event. So those events will happen, and then the first question that comes out of everybody's mind is, well, is that event becoming more frequent? And that science is actually, it's fairly new in the community. We're trying to get a sense of, is this event happening because of climate change? And
or has the probability increased because of climate change?
Right. Yes. So, for example, like with flooding, we classify flooding as probability. So, for example, like a 1 in 1,000 year event, which means, in that sense, that means in any given year, the probability of flooding to occur will be 1 in 1,000, or 0.01%. So what they're trying to get at is a type of, if an event was a 1 in 1,000 year event now, will it become more likely down the road, like a 1 in 500 year event? So it's not the easiest question to answer, and it really depends on lots of different configurations. So, for example, it's much easier for us to use like a temperature outbreak, like a heat wave or a cold wave or even drought. Those are, from a geographic standpoint, those are very sort of large in nature. And so the science is pretty sound on that, to say, are heat waves happening more frequently? Are cold waves happening more infrequently because of the changing climate? And more or less, yes, that's the case. The attribution science is telling us that. For more of these specific events, like flooding or tornadoes or just severe storms in general, those are harder because, one, they're smaller in both spatial scale and temporal scale. So like a tornado, they're only happening for, they're on the ground for, let's say, a minute or two. And, spatially, they're very small, like the biggest tornadoes are like a mile wide. So those are a little bit harder to say, like, hey, these are being more frequent. What you can say, though, is sort of the ingredients are changing. So I kind of going back and forth a little bit. Let's take flooding, for example. flooding occurs when, flash flooding occurs when there's a lot of heavy rainfall, so much rainfall in a short amount of time that, the ground can't, absorb it, or it can't get distributed away, flow away correctly. The science, we're not able to say just yet that a particular flooding event is becoming more frequent. But what we can say is, with a warming atmosphere, you have the ability to hold more moisture. So the science is telling us right now that heavy precip days, so days that have at least like 3 inches or more, those are becoming more frequent. So, we're not able to say like every rainfall event is caused by climate change, but a lot of these heavier events, like these heavy flash flooding events all across North America, are certainly have a higher likelihood of occurring because of climate.
Perfect. That was pretty much the perfect answer, I think. So to approach this scientifically, like the idea of weather events and how we interact with them and how they're felt locally, you've been looking at those detrimental effects, for example, heat waves, through a combination of probability and climate models and statistical analysis of past events. I think you called it attribution science. To rephrase, how do we explore our vulnerability to these sorts of events with respect to a changing climate? And I guess we should probably define vulnerability for the audience.
Yeah, vulnerability has many different terms to this. I know the IPCC, which is the Intergovernmental Panel on Climate Change, they define, if I'm not mistaken, they define vulnerability a couple ways. One is through kind of sensitive, part of it is sensitivity. So it's like the actual, not sensitivity. So sensitivity is one of them. But the one I'm thinking of right first is exposure. So first off, it's like direct exposure to the event. So heat, let's just stick with heat for now. So it's the actual exposure. Then there's sensitivity, which is the sort of the characteristics of who's being exposed. So the type of people, their backgrounds, their socioeconomic background, let's say, things like that. Then there's something called adaptive capacity, which is the ability to sort of survive or adapt to these types of things. So like, for example, in the Southeast US, which is where I am. So, if you want to talk about vulnerability a little bit, there's the exposure. So it's just the direct temperature that we're recording. In the Southeast US, humidity is a big factor as well. So we have, in some cases, we take into account heat and humidity. So that's sort of the exposure piece. Then the sensitivity of who's being exposed to the heat. And that could be, it's everybody, but not everybody is affected the same way. Some folks have the ability to have air conditioning, some don't. Some folks can afford it, some don't. And then you have folks that are, housed and unhoused. Are you working outside? Are you working inside? There's lots of different components to that. And then sort of the adaptive capacity is sort of the ability to withstand the heat. So do you have access to water? Do you have access to air conditioning? Do you have access to, if you are having health issues as a result of heat, do you have the ability to go to a hospital? Do you have the ability to get an ambulance? In North America, these are questions that are like mostly easy, but outside of the US or outside of North America, not everybody has that luxury. So there's lots of different components to this, and there are data sets out there that try to capture all this information. There's a lot of science that does talk about adding all three of these pieces together using data from, in the US at least, they're using like census data to get the characteristics of folks, and then are they vulnerable to these extremes? CDC. Go ahead.
Would it be fair to say that vulnerability is a function of the exposure to the hazard and the ability of the population or the person to modify behavior to that exposure, or the resilience, if you will?
Sure. Yeah, that's a good way to put it. Like I said, there's different data sets to sort of quantify this. The CDC has something called the Social Vulnerability Index. And then the Census Bureau also has their own version called the Community Resilience Estimate. Kind of like the temperature data, they have different inputs and different methodologies, but they kind of come to a similar conclusion in that, there are some areas that are more adversely affected by events than others. And this is kind of at least in the climate world, we're trying to figure this out a little bit more. We don't have the exact answers just yet, but one of the things we can say are, climate is, it's disproportionately affecting folks. Folks of lower socioeconomic class have a harder time sort of adapting to these events, and they're considered more vulnerable to current and future extremes.
Yeah, and first off, thank you for talking about this. This is not something that I could, I've many times I felt like maybe I could do a climate change episode on myself, being a geophysicist, being part of geoscience. But then I realized that, no, I just can't talk about this sort of things because I have no background in it whatsoever. And thankfully, through emails back and forth, and thanks again, you mentioned some of these topics that you're passionate about, like what we're talking about right now is integrating the social and economic information into those climate models to see how people are directly affected by them. I think perhaps depending on where people come from when they listen to this podcast, they might be more familiar with the topic of the social determinants of health. Would that be a fair, similar phrase?
Social determinants of health. Can you elaborate more on that?
Yeah, it's my understanding, again, I'm a geophysicist, but the idea is that those who have less means, so less ability to buy healthy food, are going to have a lower life expectancy. The people who have less means are going to end up living in neighborhoods that might be close to a coal power plant, for instance. So they're dealing with pollution from there, lowering, et cetera, et cetera, et cetera. So you can put the idea of how well you live is direct, or at least somewhat directly related to your social and economic means. So we're seeing that climate change also affects people in a similar way, that they do not all experience it equally because of these same determinations. So even though the language seems to be a little bit different, they're getting at kind of the exact same thing.
Yeah, no, that's true. And there is a lot of research out there that's doing that. I know we had a colleague a couple of years ago that did this for air quality, and they were showing that in certain parts of the US that they were very close to certain, plants and such, and they were there. One of the reasons they were there is because of redlining and, putting BIPOC folks and people of lower socioeconomic standards closer to these plants, which then, can create sort of these, health deterrents down the road. And there's another example where even with some of the networks that are generated. So I know, sticking to air quality, there were some networks. There's a network for air quality sites. Again, they're sort of in situ measurements, and those were also installed in sort of higher class neighborhoods. So they may not have as much, it might indicate that the air quality is good, but it's sort of in a higher economic standard neighborhood, let's say. So it's kind of the data is kind of maybe not exact. And unfortunately, it's a thing that it's been going on, not just in the US, but lots of places as well. Even rain gauge networks. We have a network here in the US, and I think partly in Canada as well. It's called cuckles. It's the Community Collaborative Rain, Hail, Snow Network. It's super amazing. It's very densely populated across parts of North America. But it's still, you have to sign up for it, and it costs, $30, $40 to install the rain gauge. They don't provide the rain gauges. And that can still be a deterrent for folks. People don't have the $40 to go buy it. So that can create sort of a disparate network of this. It's a tough problem to have. Stations cost money, and they cost money to maintain. But in all different facets of not just the networks themselves, this is a concerning issue for those that are underserved.
For sure. And I just, anybody who's listening to this and is in concern of being able to react to these sorts of events, depending where you are, your local public health or government agency might have tips and tools that you might be able to access to help reduce your vulnerability to these sorts of things. Just one completely example from my own neck of the woods, you can get, or at least last year you could, free air conditioner in BC if you met certain criteria from the government or from BC Hydro, which is government owned, same thing. So there might be something that you can access, and accessing these programs are also a challenge sometimes as well. I do understand that. So hard science and data like temperature, wind, humidity, they're bringing the complex interplay of risk, vulnerability, resilience, and to future events and everything else. That's a lot to communicate. And this podcast, to use an old and perhaps bad analogy, this isn't exactly your first rodeo. So climate change communication, perhaps to help the listeners to talk about this with the family and friends at those awkward family dinners. I think in the US context, it's always the stereotypical uncle at Thanksgiving, but it can be, use whatever phrase you'd like.
Yeah, talking about, the word climate is a dirty word. There's a stigma behind it. And it's been a stigma for a long time. And when you say that word, you basically, it's kind of a trigger word too, where, when you say it to someone that you don't know, you wonder, at least from my perspective, being a scientist, you wonder which side they're going to fall on, because it is, especially in the US, it is binary. You're either, for it or against it, even though it's not a belief system. It's based on facts and peer-reviewed science. But that's just the nature of the game. That's what happened. So people will fall on one side or the other. And what happens is you kind of, not only do you fall on a side, but you become very rigid and want to defend it. And at least in the US, it has become a political thing, a left versus right issue. And if you're not on the right side, you want to defend it. If your viewpoint differs than the other, you want to argue against it, and it can lead to a shouting match. And it's really hard to do. Kind of looping back to communication, it's important to do, because again, the data and science are there regardless of your belief. And you want people to understand that it's affecting them. One of the issues that people assumed is that climate change is a end of the century problem, or it's a polar bear problem. And it is. It's still a polar bear problem. It's an end of the century problem. But it's also here and now problem too. And trying to, again, communicate that to the person is hard to do. And there's a great book that I would suggest. So there's a climate scientist here. She lives in Texas. Her name is Dr. Catherine Hayhoe. She's a climate scientist, world-renowned. She's written a lot of reports and is part of these big assessments. She wrote a book a couple of years ago called Saving Us, and talks about this a little bit. And kind of some of the things I said earlier were based on her book. Yes, we have the facts. Yes, we have the data. Yes, we can go to people and tell them climate change is real. It's a here and now problem, but it's also important to listen. And she has done a really great job at listening to folks. And I'm going to botch this example, but I'm going to paraphrase what she said in the book, is that she went to a group and asked them about climate change. And they said, oh, well, that's a Al Gore issue. I don't believe in that. But she kept talking to them and started listening to what their concerns are. And it turns out that they had done stuff in like agriculture, and they were very concerned about all the drought events and how dry it was. And she kind of told them, she said, using the data and facts, saying that, well, these events are becoming more frequent, and this is something you have to adapt to and you have to think about. And they were kind of on board with it, even though it could have just been like, climate change is affecting this. But because climate was a dirty word to them, you had to kind of take a few extra steps to still tell them the same thing, but in different language. And I find that super important because, again, it's a dirty word. Yes, you can have arguments at your dinner table, but getting them to understand climate in a different context is hard to do, but super important for folks to understand that this is a here and now problem. And this is kind of comes back to communication, where we really need to find a way to tailor our results to every individual person to make it relatable. And that requires empathy, it requires listening skills, it requires communication skills. They don't really teach that at the college level these days. You just have to learn that over time. And yeah, like I said, it's hard to do, but super important.
And before we get to the last and most important question of the entire thing, I just want to say people should feel a bit optimistic with the way things are progressing. Are they progressing as fast as they should? No, but people are starting to take real policy changes, and we are starting to see real change towards renewable energy and the like. So we're perhaps not yet discussing the politics that we should, but this isn't a politics podcast. We're talking about the science here, not talking about what to do about it. But things are moving in the right direction, so we should feel at least somewhat optimistic. At least I'd like to think so.
Yeah, I mean, and the book from Dr. Hayhoe talks about this a little bit, where it's like there is still hope.
You will send me the link to this, I hope, so I can put it in the show notes for anyone.
I can send it to you. They ask Dr. Hayhoe all the time, is there hope? And yes, there is. Sometimes you wake up and it doesn't look great, but there are investments being made out there. There are certain things happening that are positive. It is very slow moving. It's pushing a boulder up a really steep hill, but there is hope.
All right. Now to leave someone with perhaps a little bit more of a funny bone, it is time for the traditional last question here on Whimsical Wavelengths. Tell me your favorite science joke.
Okay, so I'm a father, and fathers love their dad puns. And now for me, I don't love all the dad puns. I find them some are very silly, and I don't like them. But I thought about this one. So, my background is in meteorology. So, basically one of the reasons why I got into this business is because I love looking at clouds in the sky. So, with the help of my 8-year-old, we did this together. So the joke, and so this is their joke. I'll give them credit for it. So if it doesn't pan out, I'm going to blame my kid. Yes, I'm going to do that. All right. So what did the happy cloud say to the grumpy cloud?
I don't know.
Why so serious?
Oh, that's a good one. I'm surprised I didn't use that at the beginning of this episode. Well, thank you so much for coming on the podcast and taking us through some of the work that you're doing and the stuff that you're passionate about in climate in general.
Well, thank you for having me.
I absolutely love that conversation, especially now that I've just edited it and kind of reheard it again. We collectively need more conversations like that. Being good at communication for science is extremely important, and I'm so thankful that Jared was able to come on. To all of you listening, to grow and bring amazing conversations to more people, I need you to subscribe, to leave a rating, leave a review, and you know what? Tell somebody else about us, about Whimsical Wavelengths. Spread that auditory dose of science.
Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight. In a world so chaotic that misbehaves, melodies that echo show us six always. Colors intertwine, painting the sky. We're lost in the rhythm as the universe flies by. Oh, we're tuned in, feeling the beat of the unknown. Can you hear it? It's echoing through your bones. this melodic maze we let